So I'll start with, what's going on here? Here it is. Okay. This is a computer program which was written by Nicolau Saldanha, another friend of mine from PUC, and myself, using ideas which were developed also with the SC Malta, and it handles the most naive of nonlinearities. They are functions from the plane to the plane. For example, the function you see over there is this one. Okay, I'm using complex notation, but clearly this function is not an analytic function at all. Okay, let me tell you what that means. This is the domain, this is the counter domain. This is the set of critical curves this function has. This is the critical set of this function. Why does it look so regular? Well, you see, you started, forget a little bit about this square. If you look at this, you have a function which is doubly periodic. So you should expect a critical set to be something like a grid. But then we decided to add something which is definitely imposing at infinity. And the grid pattern essentially dissolves when you go away from infinity. Those are the images of this critical set here. Okay? Sorry? Well, this is a function from R2 to R2. You look at the points where the Jacobian is not invertible. Okay? So in particular, I'm pointing at places in the domain where the determinant of the Jacobian is positive. Now it's negative, now it's negative. Okay? Now, let's do something stranger here. Take a point over here. You see, I'd like to point at 4 things at the same time. Have a look here. This point here has 2 preimages, which is exactly what you expect from z goes to z square. Okay? This point here has 4 preimages. By the way, you must have seen that the preimages of those points here are guys coming over here and guys coming over here. The moment I trespass this red line here, there were new 2 arcs of preimages being born from this fold point here. I should remind you that the generic critical point by standard factor singularity theory is just a fold, right? You should think that this point here is mapped to that red point over there, and those 2 sides here of the domain are being taken to the same side of that point over there. Okay? I should remind you also from basic real analysis in a sense, that this map is proper, clearly, and under those very privileged conditions, the number of preimages of points on regular connected components over here is the same. So everybody over here has 2 preimages. You get inside here, there are 4. You get out again, there are 2. Let me keep moving. So we're talking about guys with 4 preimages, 2 again, do you see it? 4 again. Now I'll get in here, and I went through 2 images of critical curves. So now I have 8 preimages. If I get inside here, I have 10 preimages. Okay? In a very sturdy sense, I'm solving equations of the form this equals a given number. And of course, depending on the point you give me over here, the number of preimages is varying. I would never be crazy enough to try to write down a general theorem which handles this animal. Okay? There's a certain moment which is very reminiscent of what we do in Calculus 1. has a certain moment when you simply say that it's not worth doing the theory. You just plot the graph of a function. You tell the kids about parabolas. You tell the kids about what a cubic function looks like, but you won't be stupid enough to tell them what are the hypotheses on the coefficient of a polynomial of degree 7 in order that it should have exactly 3 real solutions. You just plot the graph and see what goes on. Okay? Let me come up with another example. This time I'm going to show you this function here. Well, of course, it looks awful, right? Because we had to expand the z's into x and y variables. Big deal. Okay. Now, what you have here is the following. Your domain has 2 critical curves. The image of those curves is shown here. And actually, there's an enormous amount of two-dimensional topology that should accommodate for what you're seeing. Just to give you an idea, 4 plus 1 gives 5, which is the number of cusps you see over here. If I'm going to show you that this actually it's a pentagon. Let me increase this. Look at the pentagon. See? There are 5 cusps on this critical set over here. Whereas here, you'll find 7 plus 4 cusps. But it turns out that the picture you see here, well, perhaps it's not exactly what you expect. It's a polygon with 11 vertices, but it's a stellated polygon. And again, there are restrictions of a Riemann-Hurwitz type, which prescribe that this indeed should be the case. Let me ask you something silly. Guess how many solutions this equation has? Okay? And we'll do it. You start over here. Everybody around here has 7 preimages as expected from something which looks like z to the 7 at infinity. 9 preimages, 11, 13, 15, and now to get closer to, say, the origin, which is exactly the center of this pentagon. Oops. Let me tell you actually what they are. Okay, there they are. Okay? So in a sense, this is what I would love to have, but now for a semi-linear PDE. Now I'll start a lecture. Well, I'll be very, very humble. I'll start actually with the Ambrosetti-Prodi situation, which you know very well. It's sort of the simplest possible nonlinearity coming up in real life, right? Well, in our real life. Oops, I'm messing up already. What's so wrong about it? Bounded domain, minus Laplacian, the eigenpairs, Dirichlet conditions. The spectrum is a bunch of positive numbers going to infinity. We take a nonlinearity which is convex with the derivative bounded in such a way that it's going to interact just with the... that's why. That solves a number of problems. We want A and B to stay strictly, to swallow lambda 1. And that's the classic Ambrosetti-Prodi theorem, right, with the reinforcement provided by Manes and Micheletti, right? You have this function here acting on U. You want to solve this equation here. Phi 1 is the eigenvector associated to eigenvalue lambda 1. And if f interacts just with the smallest eigenvalue, then there's this beautiful fact here. Depending on the value of what we call the height, right, this equation here can have 0, 1, or 2 solutions. Okay, known to the Greeks in a sense, and still it's a beautiful result. Now, it turns out that if you go through the original paper, it's written in the paper is written in a very peculiar form. Indeed, if you want, you can sort of concoct out of that this statement over here. Notice that there's no reference whatsoever to a Laplacian, for example. Okay, you simply have there I have having the usual problems with this business. You have a function between Banach spaces. Actually, the original version used Holder spaces here, right? C2 alpha, C0 alpha. And what we're saying is the following. Take a proper map, okay? In other words, infinity won't bother us. Then you look at the critical set, you cross your fingers so as to have the simplest possible critical set. It should be a connected hypersurface. Actually, what the examples all the examples people know are even more restrictive than that. The critical set is really just a hyperplane, a topological hyperplane. Now, this is the real catch. All critical points are really folds. You never see cusps, for example, in the Ambrosetti-Prodi situation. And this is actually, this and properness guarantees actually that the function is injective on the critical set. Oh, I forgot to show you that, actually let me push a bit more, see if it's worse. What I want to show you is the following. Those pictures I showed you already, right? Now, what I want to show you is the inverse of the image of the critical set. I'll bring it back over here. And it will take some time. It turns out that with the standard Ambrosetti-Prodi hypothesis, this complicated set we are going to see simply does not exist. In other words, the nonlinearity specified by the Ambrosetti-Prodi hypothesis is extremely generous. Look at that. Actually, for you to have an idea of why this should be so, let me show you. Well, instead of showing a file which by now I lost, let me indicate that this is rather plausible. Remember that the origin had 17 preimages, right? You see, one of them is just here, smack in the center of the picture. There are 5 others over here. So there are 6 preimages of 0 here. And can you see there's a little pentagon on each of those petals over here. So there are 11 preimages over here, plus 5, plus 1. I've chosen this very symmetric example exactly so that our eyes could simply understand things without much explanation. Okay. What I'm trying to convey is the idea that all I'm showing you actually doesn't come up in this very simple example provided by the Ambrosetti-Prodi situation. What a relief. Now, it turns out, actually, that there are 2 things which are sort of not convenient in this phrasing. First of all, as a numerical analyst, for example, I have very little information about how I'm going to invert such a map. Okay? The second thing is that such geometric statements are, in a sense, rather rigid. Let me provide you aspects which are going to make our life harder if you change things just a little bit. For example, very frequently you have to handle Holder issues, Sobolev issues associated to the Namitsky type linearities you add to your operator. It's very frequent that sometimes your maps go simply beyond folds because life is harder. Turns out actually that even the simplest singularity, the cusp, is something which is rather hard to detect. The very first cusp, I would say, which has been identified with precision, actually was in a paper by Malta Saldanha and myself, which is essentially this map here. So look at this ODE, periodic boundary conditions, and the claim is that there are global changes of variables here in such a way that this operator, this nonlinear operator, becomes this. Where x and y are numbers, and v is a vector which essentially pads this infinite dimensional space with the identity. The proof of such a result is quite complicated. The key point of it, again, is very geometric, and it really requires substantial generalization if we want to extend it to a Laplacian, which is the kind of stuff I'm doing now. Just to give you an example of what I mean by the necessary techniques, consider this set here. Pick the u's over here such that the integral over the circle of a function equals 0, where the only thing I know about the function f is that the roots are topologically transverse. In other words, we're talking essentially at the level set, the zero level set of the average of an Namitsky operator. And it turns out that this set is necessarily a topological hyperplane. This is not true, for example, in finite dimensions. If you were to replace this integral here by a sum, you could get spheres, tori, whatever, all kinds of topology. On the other hand, if you go to infinite dimensional, it all trivializes. The argument to prove here is essentially something from ergodic theory, and it's very general. It accommodates for example, vector versions, different spaces. It's
I can understand why you spoke about cusps there.
What I'm trying to convey is the idea that...
And I don't know exactly what are folds.
Okay.
Sorry.
No, on the contrary, a pleasure and honor. Keep in mind the inverse function theorem, right? It says that if you have a nonlinear map and the Jacobian at a certain point is invertible, then your map is locally a diffeomorphism. The very first thing that can go wrong is the following. Your derivative could mess up in one direction. You could have a one-dimensional kernel, say you have a Fredholm operator, okay? And essentially what I'm telling you is that, well, do a small Lyapunov-Schmidt composition. Okay? Derivative is essentially good in almost all directions but one, but along that direction what you see is an x squared effect. This is what a fold is, okay? You took two sides of the critical set and you bring them over here, okay? It turns out that folds are generic. Most of the time, if you choose without cheating a critical point, it's going to be a fold, okay? But it turns out, remember that the images of some critical curves gave rise to vertices. Those vertices here are actually meetings of two lines of folds. So this is where a carpet essentially goes like that along a spine of a fold, and then it meets another spine of folds here and goes over here again. So if you fold it twice like that, it might happen that at this point here, you have a point which is more obnoxious than just a fold. That's a cusp, okay? And it turns out that what I'm telling you so far is the description of the way people think in singularity theories, okay? Those are local objects. On the other hand, the Ambrosetti-Prodi theorem makes a statement which is global. It says that, in a sense, the fact that you have 0, 1, or 2 preimages is strongly suggesting the idea that your domain is being taken to the counter domain by just folding twice over a certain line. This is an idea which we will explore soon, okay? And you could do something even more perverse than that. But the point is that, again, those hypotheses are extremely restrictive, okay? The moment you jump to, for example, to the next singularity, which as we saw are abundant, okay, you start facing monsters like that, okay? And it really takes a substantial technology. Actually, it's a kind of trick, as I was referring before, which works only because you're doing infinite dimensional topology and you have more freedom to fool around there than in finite dimensions. Okay. Now, let me state another way of describing the Ambrosetti-Prodi theorem, which is much closer to, in a sense, what a numerical analyst would like to state. Actually, you should think that, instead of thinking of an arbitrary nonlinear map, okay, think that your map actually it's a linear part, which is self-adjoint, a nonlinear interaction, and a bunch of very privileged properties. For example, pick an eigenvalue here, which is simple. Suppose that the related eigenfunction is strictly positive, okay? Suppose that this nonlinearity interacts only with this eigenvalue, okay? And, well, what this is saying essentially is that every critical point of this function f is a fold, okay? And it turns out that given those hypotheses, this original map here, it's actually a global fold in the sense that you have global changes of variables which convert that map into this map here. It's sort of surprising, actually, that it took a while for people to go from this description as phrased in the Ambrosetti-Prodi theorem to this description over here. But it turns out that actually the process of changing coordinates took a while to be digested. And actually, as you can imagine, this is the very heart of a sturdy numerical analysis. Okay, I'm going to try to show you that along the way. Okay. I'm going to start with very basic geometry. Say that, I'm always having problems with this. A vertical set, my vertical subspace is going to be spanned by the eigenfunction with respect to which the nonlinearity interacts. You split your domain into vertical and horizontal, same stuff over here. Keep in mind it's typical, we are talking about Sobolev spaces, okay? This is an H2, boundary Dirichlet conditions, this is an H0, okay? Of course, we have orthogonal conditions, or orthogonal projections. And the remarkable fact is that under the hypothesis of the metric version of the Ambrosetti-Prodi theorem, the following geometric fact happens. If you take an arbitrary horizontal subspace, its image under this map F is going to be what we call a sheet. A sheet has a geometric property that it's really a graph of a function over W0. Okay? So you should think that every horizontal subspace here is being taken to a sheet over here, but keep in mind that different horizontal subspaces are taken to sheets which might intersect. The good news, however, is that you shouldn't look at sheets. What you should do is the following. You take vertical lines, okay? And each sheet is going to intersect a vertical line exactly once. From what I told you with what I told your eyes so far, right? The upshot is that if you want to invert a vertical line, what you get is a point on each sheet, okay? Welcome to fibers. Okay, the two basic facts about fibers are those. As I was telling you, if you bring back a vertical line, you get a curve which intersects each one of the horizontal sheets at exactly at one point. Okay, so fibers are parameterized by height. Actually, those are smooth maps. And it turns out that if you just think about them collectively, you can think that the set of fibers bijects with the set of vertical lines. So again, the fundamental issue here is the following. If you restrict your function f to each one of such fibers, the image is going to be a vertical line. Okay? More is true. This gives a one-liner as a proof for the Ambrosetti-Prodi theorem. Essentially, what I'm telling you is the following. I wanted to convince you that the map which goes from here to here is a fold. What I have to tell you is actually the map, when restricted to each fiber, actually acts like a parabola. If I move along a fiber, what I see on the image is the following. I'll go up and then I'll go down. And this essentially is forcing you to put an appropriate coordinate system. And indeed, the proof breaks into chunks, into elementary chunks. The very first one is this one here. The positivity of the first eigenfunction is essentially what it takes to show that the asymptotic behavior along a vertical line is correct. And actually, given the hypothesis Ambrosetti and Prodi requested, there are remarkable regularity properties, as you shall see. The requirements that the kernels of the Jacobians are positive essentially tells you that whenever you hit a critical point along a fiber, you're going to change the direction in which you're moving along a vertical line, but actually you can only do in a systematic way. You can only go from going up to going down. You can never go from down to up. And there's a third very peculiar properties of fibers, which is the fact that the moment a fiber trespasses a critical point, the tangent vector to a fiber is exactly a vector in the Jacobian of the map F. In other words, it's a natural geometric object. Well, given all those facts, let me give you some examples of what you can do with fibers. First of all, as I was telling you, you shouldn't be so afraid that your map stops being proper, because what I'm trying to convey is the idea that, listen, this is just a one-dimensional map. Okay, forget of capital F as being a map from a holder space to another. Let me say it differently. Say you want to solve something like that. G is a point here in the image. Instead of asking directly what are the preimages of G, what you do is the following. You draw this vertical line here, and first you try to identify which fiber goes to this vertical line. And this you do, I wouldn't say trivially, but this you do in an extremely robust way, because as I told you, the fibers biject with vertical lines. And there's a sturdy numerical algorithm to operate on the quotients. In other words, look at the set of fibers, look at the set of vertical lines. This is a diffeomorphism which you can handle numerically. Very sturdy. So the upshot is the following. Essentially what you do is you pick an arbitrary point here, you see where it goes. Oops, bad news, it's not over here. But still, you know that this vertical line here should be deformed over here to get to this vertical line here. So essentially what you do is local theory, which is what numerical analysts do extremely well. So you start moving from a point to another until you get to one of the points which really hit a point on this fiber here. Once you have a point in the fiber, your problem becomes one-dimensional. The only thing you have to do is you have to do a predictor-corrector method, as numerical analysts described, in order to make you move along this vertical line. But this, again, it's calculus. It's a function from R to R. It's an extremely sturdy computation. This is an example of how incredibly structured this problem is. This is a very poor man's version of this map here. What we're looking in this picture is a function which takes x and y to this map here. This is a discretization of a second-order operator, and the fibers will play the role of those lines over there. I mean, those are vertical lines. The fibers are the inverse of vertical lines. Notice, by the way, that in this example is so simple that all fibers eventually become parallel, both at minus infinity and plus infinity. This happens also for this general case here. And this was something that we first learned numerically. We faced the following exquisite miracle. Remember, I was telling you that the very first thing to do to perform these numerics is to be able to identify a point which hits this fiber here. We realized numerically that the higher we went, the faster, the higher we've chosen this point U0, the faster we would find the appropriate point U star. And it has to do with the fact that the higher you go, the less turbulence you see. Your problem becomes essentially linear. And this is indeed something that, if you check the analysis of the underlying Ambrosetti problem, we notice that indeed that's what was going on. Okay, this is a more realistic example. Take a rectangle, and now I'm going to mess up with the Ambrosetti-Prodi hypothesis altogether, okay? I'm interact with the second eigenvalue, okay? So now your ground state is not positive anymore. You're not talking folds. It's a different ballpark. Big deal. The numerics associated to fibers handle that absolutely uniformly. This is the nonlinearity. As the extreme values of the nonlinearity interact only with the second eigenvalue. And this is what we call a height map. The height map essentially says the following. You move along the fiber in the domain, so this is the height coordinate. You compute f at those points, and you see the height over here. What we're seeing here is that the height from this point goes up, then goes down, then goes up again. In particular, the point we started has 3 preimages, you see. As you know, probably, there's a whole industry which provides hypotheses on semi-linear equations in order to guarantee that with certain right-hand sides, you have 3, 5, 18 hypotheses, okay? The axis I'm trying to grind is that this is pretty much like studying polynomials of degree 7, okay? You have a numerical algorithm which handles everything. Okay, just to give you an idea of what actually, how loose we feel about the Ambrosetti-Prodi theorem now, let me give you examples of scenarios for which Ambrosetti-Prodi theorem is still true, which are sort of weakly familiar. For example, I would say Beresticki would know this. Boyan probably knows that, okay? Start with the Schrödinger operator for the hydrogen atom, for example. And if you, again, interact just with the ground state, you have a global fold. Actually, the $50,000 question is, what does that mean phenomenologically, right? Why should someone in quantum mechanics be interested in that kind of stuff? That I don't know, but I'm asking around. Actually, you can use the same geometric attitude to handle, for example, systems of equations, or maps which would be related to handling 2 atoms, for example, right? You would go to the tensor product, you would do expressions like that, and for maps like that, on those spaces here, you still have global folds. Okay, once you start thinking geometrically, everything becomes absolutely natural in a sense. Let me show you 2 other classes which belong to this ideology. The first is that we're beginning to understand what to do with non-self-adjointers. In other words, non-variational problems. André, one of the co-authors, said, no, here it is, André. Pick a matrix which is not necessarily self-adjoint. Look at a simple eigenvalue and say that the eigenfunction, the eigenvector associated to the transpose is a positive eigenvector, okay? Then again, if your nonlinearity interacts just with this eigenvalue, this map here is a global fold. Of course, it's the usual business, right? Big deal, it's a matrix, okay? So let me provide you another example. You can, if you have a function, a nonlinearity, which interacts with the bottom eigenvalue of an operator of this kind here, and this is a standard non-self-adjoint operator by now after this beautiful paper, right? You still have global folds provided f interacts with the first eigenvalue in a very tight way, okay? And actually, Boyan is willing to put his head in to be chopped, right? We do believe that we can extend this point of view to more general operators, for example. The geometry really does it for you. Let me come up with a last example, okay? There was a time in the late 80s and 90s when people started searching for folds and cusps frantically. And there was this example provided by Mandian of an integral operator which gave rise to a global fold. His map is essentially the following. U goes to identity minus this expression here. U integral a certain map f of u times a vector over here. In other words, it's a rank 1 nonlinear perturbation of the identity. Well, it turns out that with the silly geometric technology which I've been showing you, you can do much better. You can actually, well, let me fill the slide and then we'll talk about it. You can actually handle essentially Markov chains, for example. You can handle positive integral operators for which, once again, you add a perturbation which now annoys, say, the top eigenvalue, okay? And you still have an Ambrosetti-Prodi type phenomenon, okay? It turns out, actually, there's a very interesting break in this business. Let me tell you a technicality which is closer to the estimate issues. The Minsky operators are hard to find between Sobolev spaces. However, they are easy to get amongst Holder spaces. On the other hand, the kind of constructions using sheets and fibers we've been talking about, they require a global Lyapunov-Schmidt type decomposition, which is hard to get in Holder spaces. You don't get the right estimates. Essentially, self-adjointers helps you tremendously when bounding all you want. So the lucky break is the following. You have to think that perhaps you're so lucky that, well, let me give you one concrete example. Say we're talking about a map like that. And I give you a function here, which is C infinity. By elliptic regularity, okay, one point which goes over here is also a smooth function. But more than that, everybody along this vertical line is equally C infinity because you're just adding the ground state. In other words, fibers come in different smoothness conditions. Okay, once you have a C infinity function over here, everybody around here is C infinity. The upshot is that you can play the best of both worlds. You can sort of get a fiber by taking it in a Sobolev context. And then when you have to perform all the derivatives along the fibers of the eigenvalues of the Jacobian, things like that, you transplant the whole fiber to a Holder domain. And then you're in good shape. You get all the nasty Namitzki operators you would like to handle. So the moral is that we're able to obtain results of that kind essentially because an integral operator has very elementary regularity properties. Okay? Regularity gives us this lucky break of mixing the best of both worlds.